Man, you're ready to start anytime you want.
Okay, thanks very much, Sam. So welcome everybody this morning. So this seminar on how we use a range of micro and nanoscale mechanical and tribological test methods to improve our understanding about the performance and behavior of diamond-like carbon coatings. And if we have this insight from this test technology, we can develop better performing materials. So the work is a collaboration between myself at Micromaterials, Sam, who you've just heard, who was at Leeds with Thomas, and now Sam is at Coventry and Thomas is at Manchester Metropolitan. We're still working together in this area. So DLC, or diamond-like carbon, covers a wide range of different amorphous carbon films, and their properties can be tailored by changing the ratio of sp3 to sp2 carbon-carbon bonding, and also the hydrogen content in these thin films and coatings. And they typically can be produced with high hardness, low friction, they're very inert, and these are all very beneficial properties for many applications. But the thing we're interested today particularly is the performance under more mechanical contact conditions, highly loaded conditions, where the compressive stress within the films can lead to poor adhesion and durability in these highly loaded contacts. So we'd like to try and understand that. So this sort of thing has been known for quite a long time. So this is a little figure on the right from Derek Arnell. So it's going back 40 years now. So what Derek has done here is he's looked at the wear rate of DLC films as a function of contact pressure. And he's basically determined two different wear rates, a very low wear rate at low contact pressure, and then an abrupt transition to a much higher wear rate, which is obviously detrimental in applications. So we really, and that was kind of as far as they got 40 years ago. So we really want to try and understand what's going on behind that, and maybe can we develop films with different transitions, maybe, as I've kind of done a couple of different dotted lines there. So maybe we can develop a film where the transition is less abrupt, and it happens at higher contact pressure, or it's slightly less abrupt, but then it transitions to a more damage tolerant wear regime. So there's various different strategies that we can play with here. So bear in mind that the different optimum wear resistance in a coating is going to vary with the different application, and that's one of the reasons why we're doing this multifunctional testing. So we're looking at the combination of understanding how the mechanical properties tie into the performance. So one particular application of where diamond-like carbon coatings are used extensively at the moment is in automotive applications for friction reduction. So in fully lubricated contact, there's no it's not as important essentially to control the mechanical properties of the film, but there are trends in auto engine design towards downsizing, to working in low lubricant viscosity with smaller clearances, and things such as start-stop, and this increases the number of components operating in boundary lubrication or mixed lubrication regimes. And in these situations, then the surface is really important, and the mechanical properties of the surface is important to control friction and wear. And the real driver, as shown here in this slide from on the right from Thomas Polka, is that a huge amount of fuel is effectively wasted to overcome friction in automotive engines. And for environmental reasons, we really need to look at better sort of friction lowering strategies for these demanding contact situations. So in this talk, I'm going to be showing how we can perform multi-technique, multi-scale mechanical and tribological characterization of multi-layered diamond-like carbon coatings with complex architectures, and we use our NanoTest Vantage system for that. And what we're trying to do by bringing all these techniques together is to understand what is the correlation between the mechanical properties of the coatings and their tribological behavior in these different contact situations. So we're going to be looking at nanomechanical characterization by indentation. Then we're looking at sliding performance, unidirectional sliding in micro and nanoscale scratch testing. And we're going to be looking at reciprocating contacts in nanoscale fretting and also a more microscale reciprocating wear test. And we're also looking at their impact performance, and particularly for these systems, looking at the microscale impact. So the NanoTest Vantage, for those of you that don't know what this system is, this is a multifunctional nanomechanical and nanotribological or microtribological test platform that we manufacture at Micromaterials. So it's a modular system, and we can do a range of different tests, so multiple techniques. We have 2 different loading heads. We can do them in nano and micro scales, and we can do them in different test environments of temperature, humidity, moisture level, liquids, etc. So we're basically trying to simulate applications as well as characterizing the mechanical properties of materials. We're actually trying to understand their tribological behavior by designing tests that really screen out simulate these properties very nicely. Okay, so we're going to look at primarily in this 3 different coating systems. So the top one here is a so-called standard hydrogenated Dlc. So there's adhesive and gradient layers, and they're all deposited on a hardened M2 tool steel substrate, which has about sort of 11 gigapascals of hardness, so it provides a lot of load support. And the middle one there is silicon dope, very similar apart from this silicon doping. And the bottom one there is a tungsten dope DLC, essentially with a sublayer of chrome nitride, which gives a little bit more load support. So that one's a little bit thinner, but broadly they're similar materials in the sense that they're sort of 3 to 4 microns thick. They all have very, very similar surface roughness, about 11 nanometers RA. So and we've done a range of different tests on these things. And we've also supplemented understanding by a few analytical modeling with SIO software. So if we look at the indentation behavior initially, so on the left we can see some typical indentation curves on these 3 coatings at up to 40 millinewtons. So these are then under 1/10 of the film thickness, so that gives you an estimate of the film hardness. The elastic stress field is more far field, and so we use the ISO approach to determine the coating-only property of the elastic modulus by extrapolating to 0 depth linearly. So that's something we can do automatically in the NanoTest software. And on the right, just to indicate how these things are different in terms of, in this case, hardness. And you can see that the hardness is dropping off very near the surface. That's just potentially due to tip rounding effects. And there's just some numbers there down the bottom to illustrate just from those 40 millinewton curves. So in indentation, usually we look at the unloading curve and we sort of throw contact mechanics at that to determine hardness and modulus. And another approach, which has potentially not got the support it really deserves, is to look at the indentation energy, so the elastic and plastic work done during this indentation test. So if you can look on the left, you can see as you unload, you get a large degree of elastic recovery, and there's still some plasticity. So those WP and WE are measures of the plastic and elastic work done. And so we can divide, we can basically define a plasticity index as the plastic work done divided by the total work done. And you can see in the middle there, you can see that metric differs for these 3 different carbon coatings. So it's particularly the tungsten dope one has much higher plasticity index, On the right, if you can just make it out, you can see these are values taken from one of them, about sort of 300 nanometers indentation depth, where the plasticity index is effectively constant versus depth. So actually it's affected at shallower depths by tip rounding. And you can see there's a sort of linear relationship there between the plasticity index and the ratio of hardness to modulus, or strictly hardness to reduced modulus in the indentation test. And that's a very important parameter because that relates to its tribological performance, as we'll see later. And the interesting thing that I want you to note here is that this plasticity index on the tungsten doped DLC is actually really quite high. 0.47 is a high number for amorphous carbon coating, and that's somewhat similar to what you might find on a titanium aluminium nitride type cutting tool coating on cemented carbide. So this is an example, again here, for one of those type of coatings. In this case, it's titanium aluminium nitride with 67% aluminium in the coating. It's the red curve there, and you can see it's much harder than the carbon coatings, and particularly the tungsten dope you can see is much softer, the light blue curve. But when instead of plotting against depth, if you actually plot H divided by H maximum, essentially then you can collapse the curves on, and then you can more directly compare this this plasticity index. And you can see there actually that, quite remarkably in this case, that the tungsten doped card coating and the nitride actually almost overlay perfectly in this case. So what does that mean for its tribological performance? So we perform single asperity tribological tests. So why do we do that? Well, rather than more multi-asperity tests. Well, this is a very nice schematic from Kathy Vahl and Greg Sawyer. And what they've shown here in the middle of this slide is that in a typical multi-asperity contact, the apparent area of contact is not equal to the actual area of contact. And the real area of contact is actually a small fraction of that. So it's only contact is only taking place between the asperities on the surface and the slider, and therefore it becomes really quite difficult to understand what the contact pressures are that might be driving the transitions in that contact zone. So what Kathy and Greg said many years ago as well, okay, we can simplify that by a single asperity tip where we have a hard probe. In this case, we use diamond tips, and we can generate these scratch tests, and we can really understand what the contact pressures are involved that driving these failure events. And this is particularly applicable to thin coating systems such as the DLC that we're talking about here. So I've been involved in nano scratch testing for some time, and we finally got to the point where there's a standard, a SEN standard has just been released on that. So on the right is just an example of a graphic. In this case, it's from the standard, and it's showing how you get additional information by a multi-scan test, such as you have your scratch test, but if you precede that and also after that have a low load topographic scan of the surface, then you can really understand much more about your damage and what's going on in that you've created, and what's going on, and you can separate out what is elastic and plastic deformation. So we've been working at this in microdrills for some time. We started doing this in 1998, and got some clever things in terms of leveling and compliance removal in the software. For these materials, we've performed nano scratch tests with a sharper, so still much blunter than a Berkovich indenter, but a relatively sharp spherical probe with an end radius of 5 micron. And we ramp load to 500 millinewtons. And in micro scratch tests, we've done a similar thing, but with a blunter probe, 25 micron end radius, and ramped up to 5 newtons. So rather schematically, so if you think about this as in an indentation contact rather than a scratch, you can think potentially that your probe radius really is going to impact on where the stresses are going to be located in the coating system. So this is a very schematic way of looking at it, but essentially you can think this is why you use a sharp Berkovich diamond with an end radius of about 50 nanometers, because you want to measure the coating properties. So the stresses for plasticity are located within the coating. With a 20 or 25 micron probe, then you're going more towards the micro scale, and then your stresses are going to be located near the interface. And if you have much blunter probes, of course, then your stresses are going to be your von Mises stresses are going to be deep into the substrate, and the substrate contribution to the overall response is going to be much greater. Okay, so if we look at some experimental data, so this is now with nanoscratch tests with the 5 micron spheroconical tip, and there's the 3 coatings, and on the left you can see the hydrogenated Dlc has the highest load for yield, so it stays elastic much longer, but it has the lowest load for cracking. Conversely, on the right, the tungsten doped Dlc has the lowest load for yield, but the highest load for cracking. In fact, it didn't crack before the 500 million Newton peak load of the low load head we used for this was reached in the tests. And the silicon doped is somewhat in between. So there's a clear correlation between the mechanical properties of the system, between the coating hardness and the other mechanical properties, and this critical load for plastic flow. And there's also a correlation between the plasticity index and the onset of cracking in these systems. So we wanted to say a bit more than that, really. We wanted to say, well, actually, I really want to try and understand what's causing that. So we talked to our friends at Norbert Schwarzer and Nick Beerwich at SIO, and we collaborated with them. And now we have this as a module within the NanoTest software. It's a possibility to integrate with the SIO software, in this case, the Scratch Stress Analyzer. And this is an analytical approach that allows you to simulate the stress distributions, and that can help you explain what's going on in these scratch tests. So the input parameters are basically the indentation data, and you also need the scratch data, and you also need to know the relationship between the hardness that you measure in the indentation test and the yield stress. So this constraint factor is actually quite important when it comes to simulations. So we have a sort of internal database of these things that we can look up, and we can get a lot of things out of this. We can get von Mises stress distributions to the onset of plasticity. We can look at normal stresses in the scratch direction, which are responsible for cracking, and we can also look at the interfacial shear stresses and therefore understand the sort of bonding strength of the coating substrate interfaces. So it's a very useful multifunctional modeling tool. So this slide shows essentially simulated von Mises stress distributions at the exact moment at which the coatings yield. So they're different loads in each case because they yield at different loads. So the scratch direction is from left to right, and we've removed the indenter at the top for sort of clarity. And the dotted line is the coating substrate interface. So what you can see is that the overstressed area is kind of like a dark hashed region. And that overstressed area, you can see on the diamond-like carbon, the hydrogenated one on the left, that's actually in the substrate. So it's the coating itself is not yielding plastically. For the softer systems, and particularly for the tungsten dope one, you're getting yield completely different situation. It's yielding at lower load, and it's yielding in the coating itself. So that's very informative in terms of how you might understand and try to optimize these things. So we thought about that, and it took us back to some tests we'd done a few years previously when we'd done some nanoscale fretting tests on these coatings. And in those tests, we used the same nominal probe geometry. We did 4,500 cycle reciprocating nanoscale fretting tests. and at 100 millinewtons. So we can use the stress distributions that we simulate as an indication of the initial stress distribution in the nano-fretting test, because the conditions are the same. And what we can see under these conditions is that essentially it's suggesting that in an ideal, it's elastic for the DLC on the left, and nearly elastic in the middle, and more extensive plasticity yielding on the right. And actually, that relationship actually ties up with what you see experimentally. So the wear is low on the hydrogenated Dlc, where you're always get a little bit of wear through sort of roughness and the like. Relatively low on the silicon dope, but it's higher on the tungsten dope, and you can just see an experimental result from a paper back in 2013 there. So again, the modeling is able to explain the experimental result. So under those conditions, the load was relatively low, and there was a clear correlation between the mechanical properties of the coatings and their resistance to wear in the fretting test. So that's because plasticity was a dominant factor, much less cracking. If you take the load up, the severity of the test increases. And this is an example, in this case on the silicon dope DLC. So this is looking at the normal stresses developed at the lower critical load for cracking, which you can see in the SEM picture there is a sort of cracking at the back of the probe. So it's this sort of semicircular cracking at the back. And what you can see if you look at these stresses is that they're compressive in front of the tip, and they're tensile, they're red if in the rear of the sliding probe. The maximum is slightly off axis, but for practical purposes, you can just use these center line axes plots as shown there quite easily. And you can look and start to compare these different systems. You can compare different radii. And there's some certain similarities between the stresses that you get in these different nano and microscale tests. So their maximum values of the range are sort of 5 to 7 gigapascals. There's really very high stresses that these coatings can be subjected to before they fail. So just to compare now, if we compare the critical loads and these LC1 and LC2 critical loads for cracking and total film failure. This is from the microscale tests. And what we can see here is that the hardest coating is the DLC on the left. That's actually not the best. The worst is the silicon dope one, but the clear winner is the tungsten dope DLC. So that has the highest plasticity, and it's quite interesting to try and understand that. And so we looked at that a little bit more, and we looked at von Mises stress on the left, and what we can see, the von Mises stress is developed at this LC2 or total failure. The failure is clearly, there's some tensile stress, but there's also this substrate yield on the just at the substrate side, essentially, of the coating substrate system. And it's much more extensive on this tungsten dope DLC. So that is telling you essentially that if you've got more plasticity, then you're potentially going to get less of those stresses are available to create cracking. So maybe that's why you get these much less cracking actually that you see on failure for the tungsten dope than you do the other materials. If you look at shear stresses at the interface, actually, even though they're different adhesion, they're actually relatively similar in this case. And they're about 50% of the values that you might find on a cutting tool coating. Another thing we looked at is we looked at interfacial. We looked at the measured friction and whether we could understand what were the different components in that measured friction and how that changes as a function of load. So we apply a simple Bowden and Tabor type relationship. The total friction is the sum of the interfacial and ploughing components. And in an elastic regime, the load should be supported on the front and the back half of the sliding probe equally. And that equation that you see rather complicated there, that factor of 2 then is removed and it changes to 1. And then we should be able to, under those situations, we should be able to calculate the friction. So this, and also once you are getting plasticity in that coating, then essentially the friction can rise more rapidly. So we tried to model that. So these are on the right, you see the experimental frictions and how they, friction coefficients and how they increase with increasing ploughing for these different coating systems. So on the left, we're looking at this parameter in that equation that, as I say, is going between 1 and 2, and it varies with the amount of scratch recovery. So this is some experimental data that we published a few years ago on the left, and what we haven't published essentially is what we can do with that additional information is that we can actually try and fit the experimental friction versus load or depth data. And actually we can fit that very nicely. So those are the 3 different coatings, and we're fitting those with different different interfacial friction essentially. So it's quite nice. But I mean, the real proof of the pudding of this approach and whether it's really going to work is whether we can use exactly the same numbers to fit the nanoscale friction. Excuse me. So this was with the 25 micron probe. So now can we get the same thing with the 5 micron probe? And so we've done that, and you can see actually the agreement's not too bad. It's not perfect. You've got some surface roughness effects. You've got a transition in probe geometry from the spherical part towards the conical part. But overall, that is, I think, particularly encouraging agreement. So that kind of suggests the approach works. So to sum up the part on scratch, go back to this initial sort of Derek Arnell plot, and we can sort of understand maybe or suggest what might be behind that. So if we take initially the black line there as being representative of the hydrogenated Dlc, it has low wear at low contact pressure because it's controlled by this ratio of hardness to modulus or yield stress to modulus. And then once you get plasticity in the substrate, once you get cracking, then you get this transition to this much higher wear rate. The tungsten dope clearly is better. It clearly can handle a bit more contact pressure before it goes, and when it goes, it gets less dramatic, potentially, at least in highly loading scratch, not so much in the fretting test, the pressures are not as high. So and behind that contact pressure, I think what we maybe need to, what the scratch test is, what the modeling is telling you, actually the depth of the peak stresses are changing as well. So this is maybe a useful way to look at this and understand what's going on behind these systems. So this sort of information is giving you clues about how you can design coatings to minimize these dramatic cracking events when they start at high load. So more recently we've done a little bit more in this area with a new module that we have for the NanoTest. So this is the Nano Tribo test. So you can see the stage there on the right, and it's a reciprocating test which allows much higher track lengths. This extends the range of the tribological tests we can do with our NanoTest Vantage system, and you can do that, not for this thing we haven't, but you can combine with electrical contact resistance measurements, and that's particularly useful for doing things looking at, for example, for studying the endurance of sliding metallic connectors, as in sort of iPhones and the like. So just to give you an indication there's different conditions in terms of probe radii, load, speeds, etc., number of cycles. That what we're doing with the Tribo test is extending the range of these different test techniques. So it allows us to slide much faster while retaining the nanoscale precision in the test. So the sort of thing you can get out of this is you can monitor friction throughout the test. So this is some sort of friction. The raw on the left is raw friction versus, in this case, sliding distance. And then we convert some of these friction loops, these friction traces to friction loops. And this is just an example where we've looked at, in this case, we've taken 4 cycles out of a 500 cycle test, and you can just see sort of graphically that how the friction has increased through that test. And in the software, you can determine how the friction coefficient varies as a function of cycles. So this is just an example for the hydrogenated DLC, showing that although typically you might think, well, the friction on DLC is always about 0.1. Well, it may be mostly about 0.1, but you do get a lot of changes that are load dependent, depending on how much micro wear, how much plasticity and things like that, how much ploughing out. All of these things can be very load dependent. So here's an example. In this case, it's a snapshot near the beginning of a test. And in this case, at 500 millinewtons, this coating actually undergoes an abrupt change in friction in all of those 3 tests. So there's something different about the third one. So you can see the much more jagged behavior in the third one. So we try to understand that, and we use some microscopy. In this case, again, with Manchester Metropolitan University, and what we can see here essentially is that there's partial failure of that DLC coating system, and you can use EDX to show that you're getting failure between the interlayers in this coating system. So it's a brittle failure, and this is a sort of inherent headache, if you like, with DLC coatings, is that they're amorphous and they can crack easily under impact conditions. So if you think just in general of a brittle system subjected to a single impact, then you can create a lot of cracks. And if you subject that system to multiple impacts, well, then you can imagine these crack systems joining up and that leading to material removal. So the lateral fracture is a critical thing, and then the growth of these lateral cracks and then coalescence, and then that causes material removal. So we study that in our patented nano impact test in the NanoTest. So you can sort of very, very schematically on the right, you can think of it just like a woodpecker, and that was an initial name for the test, as a jokey name for it when it was first developed. So the woodpecker is tapping away repetitively at the same position, and eventually you get material removal. And that's the sort of thing that we're simulating in the test. It's a very tunable test. It allows us to, we can change the probe material, impact force, impact angle. We can really understand how these coatings behave in these conditions. So if we do, in this case, microscale impact tests over a range of different forces, so it's not only the force that controls the impact, it's the accelerating distance as well, because it's really impact energy that's going on. So in this case, all of these, in all of these tests, these are 75 impact tests where the probe has been accelerated over a 40 micron distance at these forces. And you've got 5 repeats essentially. So what you can see here is, in this case, that neither of these 2 coatings are doing very well. Actually, on the left, the hydrogenated DLC, there's a couple of 2 of the 5 tests. It doesn't look like it's failed as badly, but essentially all of the other ones, there's failure, and you can see that failure progressively increasing through the test. But the nice thing about this test is that we're not reliant on these microscopy results. We've actually got data behind that, and we can follow cycle by cycle how these coatings deform, and that's very useful. And really, that's the sort of information that allows us to understand and optimize these coatings for different applications. So again, to sort of zoom in a little bit, you can see actually the interfacial failures are really at the heart of the problem here for both of these 2 coatings. And when you do get some interfacial failures, then the EDX is telling you getting sort of substrate exposure, if you like. So this is clearly an area for optimization in this coating system. The tungsten dope system is much more impact resistant. So if you can look on the left, you can see some small radial cracks emanating, and on the right, It's a backscattered SEM image, and this is one of the very few where we actually generate any sort of lateral cracking at all. And you can sort of see there are some lateral cracking between a couple of those radials, but it's not expanded beyond that. And that was at very, very high load and very unusual. But for the most part, this cracking was completely avoided. So, as I say, we can monitor the test depth throughout the test, and when we want to compare across different materials, then we initially thought that the final impact depth was quite a nice thing to try, and so on the left there we can see the differences in final impact depth between the three different coating systems, and clearly we can see that the one without the lateral fracture, the tungsten doped DLC, is much more impact resistant, but it's perhaps more informative, and it allows us to compare between different materials at different loads, and also even different substrates potentially, is to look really not at the final depth, but the change in depth through the test. So if we set the depth at the first impact to be 0, and then just look at what happens then we can really start to understand what's going on in this system. So yeah, on the tungsten doped, again, the values are very low now. So you can see that the elastic components have all been removed, and the silicon doped is clearly the worst, and the hydrogenated at the low loads showing a large scatter because it was failing in some of those tests and not others. So very, very clear differences. So just a slight aside here. This is some work of Sam's, where Sam deposited another set of samples, in this case 6 samples, and 2 of them were very similar. So the DLC and the silicon doped DLC were very similar. He also deposited it on softer substrates, which had much less load support. And for the tungsten doped one, in this case, there was not the buried chrome nitride sublayer, and that was quite a useful change, because that allowed us to be sure then that if we get the same changes on the same sort of behavior, then we can be sure that it's not a clever trick due to this buried layer. It's really down to differences in substrate in coating plasticity. So what we wanted to study in this test was to understand the influence of coating mechanical properties on erosion behavior, impact resistance, and try and understand if there was a connection or correlation between these 2 type of tests. What was the influence of the substrate, and could we replicate the erosion mechanisms? So if you look on the right, maybe you can just about make out, in this case, Sam's plotted the hardness modulus ratio as a function of depth, and what essentially you can see is on the softer substrate, the mechanical properties of the coating system drop off quite dramatically compared to the hardened tool steel, because of the less load support on the softer substrate. So these were sand erosion tests. So bottom left shows the sort of grayscale image is a optical image of the surface during a test, which has some partially removed areas and partially not. And Sam developed a pixel counting method where essentially he was able to define a level at which he could decide whether it was eroded or not. So that's indicated by that red region there. So that these images could then be statistically analyzed. And what Sam found from this method was that on the stainless steel substrate, none of the coatings did very well particularly. So in about 5 seconds in this case, almost complete removal of the coating system. So much more durable on the hardened tool steel substrate, so the similar substrate to what we've been looking at previously. And what we can see here is that the coating C system, so the tungsten dope system, is much better. So it's much more durable. So we don't get eventually, even running that test for a lot longer, and you're still getting nowhere near the same level of substrate exposure. So so again, it's telling us that it's not a quirk of having that chrome nitride layer in there. Actually, these are the only tests I've shown so far. We're actually looking at the damage as a function of impacts. So on the left, we can see this is for the hydrogenated Dlcs, and what we can see here is that when it's deposited on stainless steel, we're punching straight through that coating system. So it's a sort of eggshell failure. So it can't cope at all with the soft, the plasticity in that substrate essentially, and the coating can't handle that at all, and it's cracking. Much more durable on the hardened tool steel substrate. And if you look on the right in detail, you can see again that the red curve is the tungsten doped DLC, and that's much more impact resistant, whereas the other two coatings in the yellow and the black are failing after about 15 impacts or so in this example. So there's a clear correlation between our impact test results and these erosion tests, which we've sort of thought over a number of years, but we've not been able to check. So it's a very nice piece of work from Sam, able to really confirm that in practice. So recently we tried to simulate all that, and that table there looks a little bit sort of complicated. So getting behind that, I've just tried to simulate in terms of one of the parameters we can look at is the hardness modulus ratio that is popular in tribology. And what we can see is in the different tests, we can see whether increasing hardness modulus ratio is beneficial or not. So it's beneficial to wear resistance in reciprocating tests. It's clearly not beneficial for these hard carbon coatings on tool steel. It's definitely lower H over E is beneficial there. In terms of friction, it tends to be good in terms of decreasing the friction coefficient, but clearly in the reciprocating test that you've seen at high load particularly, there's a transition towards higher friction when you're getting some failure there. And it's useful in terms of keeping systems elastic, so the critical loads are much higher. This is related to h cubed over e squared in the system. When you go towards the microscale, I didn't say much about that, but actually it's much less clear because now the system stays elastic until the yield is in the substrate, and because the substrate is the same, actually then the critical load dependence decreases. It's much less clear. But at the nanoscale, there's a very clear correlation between this critical load and H over E. When it comes to the failure loads for cracking and delamination, then it's clear that on this coating system at least, that increasing H over E is really not helping you. So hopefully I've given you an indication about when we start to use multifunctional tests, then we really deepen our understanding about why coatings really behave well in some conditions and not others. So somewhat cheesily, you could say you could see more from a vantage point with our Vantage system. And a sort of take-home message would be that particularly for carbon coatings on hardened tool steels, if you're designing for highly loaded sliding and repetitive impact, you shouldn't always aim for very high hardness, because if you're increasing your susceptibility to cracking. And yeah, so that I think that's probably it. I'll just say that hopefully that was of interest, and I will open it up to back to Sam, I think, for questions.
Currently, we've got one question from Krishna, which is, what typical frequencies of striking are there in impact testing?
We have two different ways of doing it. The one that we were doing here is a low frequency test where we're doing one impact every 4 seconds, and the reason why we're doing that is so that we get that full depth versus time information. So we want to retain all of that for understanding cycle by cycle, each individual. So it's very different to a sort of, we can also do sort of high frequency impact tests, but in this case, we could differentiate, for example, between an impact, something where it fails after 10 impacts and 12 impacts or something, and we know exactly the depth it fails and all. So it's these things are accelerated tests where we're specifically designing. So it's not particularly the frequency we're trying to control, but it's the strain rate. So that's you can do repetitive tests in indentation, but they're typically in like multi-cycle loading tests. But the strain rate there is low because you're already in contact with the surface. So the difference here is that we're really able to simulate the high strain rates that actually occur in these applications, because the coating failures are strain rate sensitive, as Professor Bazarkis of Thessaloniki and others have shown.
Okay, thanks, Ben. So if anyone else has any questions, please go ahead and type them into the chat, and we'll answer those. Additionally, what you'll all see down in the bottom left is a little link to Micromaterials LinkedIn page. If you'd like to visit that, I will change this over in a few minutes to the Micromaterials website, which has further information on the techniques that have been discussed today. So we'll just hang on for any additional questions coming in. Okay, we have another one from Krishna there. What thicknesses of DLC coatings can you look at with nano or micro impact?
On the smaller scale, we've gone right down to 5 nanometer TAC coating systems. So that, and under those situations, these are protective coatings looked at for MEMS applications where they're put down on silicon. And under those conditions, we found, depending on probe geometry and the type of loads we use, then we were either sensitive to coating failure or to failures induced by by phase transformation of at around 11 gigapascals in the silicon substrate. So at the smaller end, right down to about 5 nanometers. On the top end, well, you've seen up to 4 microns, and these DLC systems are particularly brittle. So I think you could certainly get some useful information out of even thicker films than this if you could deposit them. Yeah, for oil and gas applications, we have looked at thicker films. I can't really say more than that, so pretty much any DLC thickness you can imagine would be testable by this test technique.
Question from Manuel here. Is it possible to study the influence of the thickness on a DLC coating with this approach?
Yeah, I think it is. I say we did on the MEMS work. We did spend a lot of time a few years ago. I didn't talk about that today because it's quite different. But yeah, the influence of thickness was in that case quite important, because the failure of the system in many cases was down to this substrate failure. So the thicker coatings in that case could provide additional load support. In terms of thickness in general, yeah, it's sort of it depends how the system fails and where those stresses are and what's the first. I mean, compared to a scratch test, I think where sometimes you see behavior is very strongly affected by thickness. Impact test may be less so, which is kind of useful in a way. It means that if in sort of commercial application where you might, for example, have comparing coatings from different vendors or something like that for an automotive application, then they don't have to be exactly the same thickness for direct comparability. Whereas in a scratch test, I think you have to bear in mind that different thickness can clearly affect the stress makeup more clearly. So it's kind of a useful thing in the nanotest, the way that you can, with the impact that you can change these things. I didn't quite get it across, but we have the ability to do nanoscale impact tests as well. I only talked about the microscale ones here, but because we have this ability to nano and microscale impact, that enables us to cover that entire range of thicknesses.
Thanks, Ben. So we have another question from Krishna, who asks, what are the typical probe geometries for impact testing? How long do they typically last on DLC?
I would say very, very sharp geometries sometimes can run into trouble on carbide type coatings and carbides. So that was one of the reasons why we went towards microscale testing, because then you can use blunter geometries. Having said that, on the DLC systems, when I first started looking at this many years ago, I was worried about this. So I was looking at two different carbon coating systems, and I did a complicated test array basically to convince myself that there was no tip wear throughout this entire test, and there wasn't in this case, even with a very sharp cube corner. I think part of the reason why tip wear is not a problem for DLC is because they're very smooth. Typically, they're hard but smooth. I think in general in indentation, the worst thing to try and indent is a diamond coat, a diamond piece of CVD diamond or something like that, because it's hard and rough essentially. So DLCs typically are rather smooth, so they are not a challenge for tip geometry at all. It doesn't change in our experience, which is maybe a little bit surprising, but.
Okay, two questions here from Abquat, who says, thanks for the great talk. First question is, what was the silicon content in the silicon DLC, which have been tested in this case? And two, how do you think internal stresses, specifically in the case of the amorphous hydrogenated and silicon doped DLC, affects the performance?
I'm afraid I cannot remember what the silicon content was.
Just
Sam, you might have a thought.
I'm just having a.
Yeah, I think internal stresses are important. I think you need a certain amount of compressive stresses in there, but it's this so that is very important. But equally, it does seem a little bit unsuccessful. We certainly. I mentioned Professor Vazakis and his team at Thessaloniki. They've done a lot of work looking at using nano impact on a range of different cemented, titanium aluminium nitride type coatings on cemented carbide, where they specifically changed the internal stresses, and then they looked to see how they behave in cutting tool tests and impact tests. Encouragingly for us, there was an absolute one-to-one correlation between the behavior of in the impact test and the cutting test in several of their papers. But also, in terms of compressive stresses, there's a sweet spot, if you like, but you need a lot of compressive stress in there. But if you have too much, then you run into bother, and particularly if you have amorphous systems, because then you don't have any sort of crack deflection mechanisms that you might get in, for example, multi-layer coating systems that allow you to avoid crack propagation. Crack deflection is a good mechanism, and so I think that is an issue with these silicon and silicon doped and the hydrogenated DLC. So certainly also I would say we've looked at a lot of different hydrogenated DLCs over there, and none of them have been particularly good. Probably the best would probably be from tier coatings, because they have graded their DLC, so there's some structuring and a little bit more, that particular grading system is a little bit better than others maybe, but certainly amorphous carbon without hydrogen in the systems we've looked at have been better, so that's another point.
I just Sorry, Ben, just returning
See on
back
the
to question 1 there in terms of the silicon content. So I can't remember whether we have figures specifically for the silicon doped that was, the sort of the original silicon doped DLC, but I do have the data for the
for
silicon
the other
doped.
ones, yeah.
Yeah, for sort of my ones, which are extremely similar. So at least measured by EDX with a fib cross section, it was for both the hardened tool steel and stainless steel. There was approximately 20% by atomic composition of silicon, and then also between 6 and 7% oxygen, because this was the silicon doping was achieved by HMDSO, which contains both silicon and oxygen. So I hope that's useful.
Yeah, I think it sort of backs up what people are finding about these silicon doped DLCs is they're good for friction. They're relatively less good for wear. I think possibly high temperature applications is where they will win out because they do have better thermal stability than the standard DLCs. So I think there's still some space there. So I didn't really talk about it, but a lot of these tests we can do at high temperatures. So we have done, for example, high temperature sliding microscale scratch tests or nanoscale scratch tests and things. So it's all possible. It just takes a little bit more experimental care and design. So.
I have a question from Dr. Baratish. Will there be any residual stresses? I presume that he's talking about generally with DLCs.
Yeah, I think these are definitely stressed. We didn't measure them in these cases, but I think typically yes. I think typically they're going to be of the order of, a few gigapascals compressive, potentially. Yeah, I think the stresses are important, and it is something that if you do measure them, you can incorporate those into modeling as well, if you like. If you have more complex modeling, as I say, the modeling what we were trying to do here was just to understand some of the basic features, but you certainly could design some more clever models if you like. You could we treated the coatings as monolayers, and you certainly can. Yeah, so this is related to that. So this
Yes.
software is, we have it. The company SIO, they are they do sell their own software, but also within our NanoTest system, you can it's integrated to that as well. So you can get it. We can integrate it for our nanoscratch data as well. So. But otherwise, just the SIO. There's a website, www.siomec.de, and you can go and get the information from there. So they're an impressive company. So I'd recommend people have a look at that as well.
Yeah, I'll find the link for that in a moment and put it into the chat. In the meantime, I have another question here. There we go. So what is a I presume suitable material for indenting DLC before it meets the substrate material?
In all the tests we've used diamond indenters, which have been fine, and that I think is useful for these small scale tests because you don't really get transfer films and things like that on the indenter side, so you don't have to clean the tip between tests and things like that. So there's no indication that you're getting any effective tribo film formation on the indenter side. So that's it is something that you could look at. For example, in future, you could do reciprocation tests with different indenter materials, and that might be quite informative. But in general, I wouldn't worry too much. It will be an issue in terms of high temperature scratch tests and things like that. If you want to go much above 500 degrees, you need to consider whether your diamond is is going to be thermally stable or not. So there are other materials potentially you could use for those very high temperature scratches. But I think up to about 500, I think even diamond would probably be okay. Because they're quite large radius probes, so they be relatively small tip wear due to diamond degradation.
Okay. Question from Chris says,
I just
Do you have
mentioned
an
that in passing. Yeah, they were all. We used the NanoTest in that first scan of the scratch test, the multi-pass scratch test. We can use that to get surface profile information, and we did that, and it was about 11 to 12 nanometers RA for all three of the first ones. Sam, you certainly looked at your set as well, didn't you?
Yes, I can look at those. So I think for the first set, so it was 10.9, 11.3, and 11.5 for the hydrogenated silicon and tungsten, respectively. I'm quite sure I do find that quickly in that paper.
But I think relatively small, and I think that's one of the reasons why mechanically they're reasonably easy to test by indentation. So the high roughness tends to be a little bit problematic for nanoindentators. The nanotest system has a certain lateral rigidity, which means that it's much less affected by high roughness samples, but everything's going to be affected to some extent with very high roughness materials.
The roughness is, at least off the top of my head, relatively similar. I think probably a little bit rougher, but I can't recall a figure at the moment. But
yeah, I think that's probably worth saying that the roughness of these DLCs tends to be down to the effort putting into preparing the substrate prior to deposition. So if you've got a relative, if it's well polished, then I think the DLC will be it'll be close to conformal essentially. So I think not quite maybe, but it certainly won't be massively rougher than the original substrate that it was put on. So
there we go. Let's look at the time. We're at 5 minutes past the hour now, so we could do maybe one or possibly one last question if anyone else has anything else they would like to ask. Just one moment. Although I think I get the impression that most questions have been answered, so I think we could wrap up there.
Well, thank you very much for your time, everybody. I hope you found it useful.
Yep. Thanks, Ben. Thanks for another great talk. Yes, and thanks for attending, everyone. So yes, we'll see you at another micromaterials webinar sometime soon. Keep a lookout on the LinkedIn page, as they will all be advertised there. So, okay.
I would say as well, we have micromaterials have some events coming up as well, so please check out our LinkedIn for those. I think the first of which is we have a tribology focused meeting on the I think it's 13th of December. So it's going to be 10 o'clock start Central European time for that one. So that's free to attend if anybody wants to. I don't know if you could either put the link in the chat, Sam, or alternatively go to our Micromaterials LinkedIn page. There'll be information there, I'm sure.
I think with that one, just ironing out a few final details before the registration link gets generated. So that will be one. Please keep an eye on the LinkedIn, everyone, and we'll share that once all the details are there.
Excellent.
All right. So thank you very much, everyone. And with that, I'll end the session. Okay.
Okay. Bye-bye.
Bye all.